to the reliability-driven mechanism design. Because Professor Gilbert, I just met him the day before yesterday. He's very, have a lot of great ideas, and he's very active. He said he's married to his university, and he tried to looking for a lot of international collaboration with any opportunities. So I think because we have Professor Gao here, and we have Professor Osawa here in Japan. Professor Cho is also our member working in Technology University, and Professor Tai, he's our vice dean. Thank you for you guys coming, because it's like early in the morning, so I'll still always sleep until 12 o'clock. But it's fine, because I still will share slides on our website to share to everyone, and he will join all the conference even today and tomorrow, so maybe we can have a lot of discussion later. Okay, so how about we just welcome
Great. All right, good morning, everyone. Thank you so much for the invitation to come and speak. So I'm going to be doing just a high-level overview of some ideas and some of the important things we need to consider as designers in doing realizability-driven mechanical design. My background is in mechanical design. I did my bachelor's and master's degrees at the University of Alabama in Huntsville, which is one of the universities affiliated with NASA in the United States. And I went to industry. I worked in aerospace and defense. Went back to get my PhD from the University of Illinois at Champaign. And then I was hired as a professor at Texas A&M in 2021. Hopefully up for tenure next year, an associate professor. We'll see. Okay, so the main overview of this talk is going to be related to exploring how realizability connects design intent to physical implementation. I'm going to define what realizability means in some depth as we go. The core idea here is that design excellence does not only equal creativity and optimization. You also have to make sure that your ideas, as elegant as they are, your ideas can actually be made into something useful in the real world. That is extremely important. That's what we mean by realizability. If we go into the civil engineering side and look at something like this AIA framework, design for integration, design for community, design for ecology, design for water, all of these can be applied to all design areas, not just building design or town layout design, but also these can work with manufactured products, consumer products, systems, autonomous driving, cars, and the software controls that go behind that. The basic idea is when we are working as designers, we have to make sure that we consider what is going to be required for our design and our ideas to be useful and actually implemented successfully in the real world. Unfortunately, this is a really big area of gap in the design space. All right, great ideas and unrealized potential. So many advanced designs underperform not because they're wrong, but because they're unrealizable. If we go back and look at the history of design a little bit, one of the things that they started noticing back when they started building rockets and aircraft and all of those things in the 1950s, 1960s, this is all over the world. One of the things they found very quickly is that designers can design things that are really nice, but that are not manufacturable. This came into a concept called the design manufacturing mismatch problem. In the 1990s, when computers were starting to become more capable and new design methods were starting to be implemented using the various mathematical models that have been built, they said, all right, well, we have advanced manufacturing processes, such as additive manufacturing, 3D printing, and all of that. Why don't we take the capability of computers and the capability of the manufacturing processes, develop both, and hopefully they'll converge together, and then we'll be able to manufacture anything that we design. Well, come to the current time, it turns out that mismatch between design and manufacturing is actually bigger than it was before, because the design methods advanced faster and more, advanced at a faster pace than the manufacturing methods. It's especially a problem now that we're finding that additive manufacturing is not as capable as we thought it could be. The technology development is kind of plateaued. So now we need to go back and we need to say, okay, how can we actually look at design from a perspective where we're keeping realizability in mind? Okay, here's some examples. Say it's a topology optimized bracket that's impossible to machine. There's a lot of work published on topology optimization now related to putting in manufacturability constraints. I'm very happy to say that a lot of that work is actually citing some of my early work in constraint mapping. Vehicle subsystems misaligned due to tolerance drift. One of the things that you find is you have a major tolerance drift problem. Any of you who do a lot of work in machining, you know exactly what I'm talking about. When you have a whole bunch of parts interfaced with each other, you have a tiny bit of error in the first part, and it stacks with the error in the second part, and it stacks with the error in the third part, and by the time you get to the end, you don't have a successful subsystem. Or the subsystem itself can be built, but the whole system can't because the interfaces at both ends are wrong. Additive manufactured parts fail due to support removal or warping. Maybe you didn't have the proper settings in the manufacturing process to actually make the thing. So, the gap between what we model and what materials and processes can deliver. We're going with the idea we need to understand the design from this perspective. We'll never completely understand the requirements because requirements are defined by humans, and humans do not always speak the same design language. So two people may be saying the same thing, they mean two different things. We have no perfect materials. All materials are defective. All materials have issues. If you go back and look at the beginning of fracture mechanics, Griffith, he was an aerospace engineer in the UK right after World War II. One of the things that he discovered was that when you had welded ships that they used a lot in the Second World War, when they went to really cold water, the welds would actually fracture and the ship could sink. You also had airplanes that had square windows that were fracturing and the planes were just falling apart in the sky. So he started going through and saying, okay, well, there must be some reason why the materials behave this way. His theory was that all materials, no matter how good they are, even single crystal materials that we use in, say, a silicon wafer, has some level of defects. His initial experiment was he calculated what the tensile strength of steel should be based on the molecular bonds, and then did tests on it. Well, it should have been 10 times what it actually was. So he came up with a theory, all materials are defective. We're going to use that for doing design. We never get what we actually design. Even with factors of safety, it can cause us problems. What do we mean by realizability? So, realizability is the extent to which a design can be physically and functionally achieved with available processes, resources, and environments. Unfortunately, a lot of designers go with the idea that, well, let me take an aside here. Have you all heard the joke that the architect's dream is the engineer's nightmare? So designers come up with things that absolutely are impossible to actually build. They look so beautiful in the simulations. They look so beautiful on paper. But when you actually try to build it, it isn't actually buildable. Looking at this as designers, the extent to which a design can be physically and functionally achieved, that doesn't necessarily mean that it's optimal. That just means that we can make it happen. This is an important perspective because I feel like one of the things that is slowing down, say, the implementation of driving cars and large-scale autonomous systems is that they're trying to go for a perfect system and trying to fix all the problems along the way. When what they should be doing is just saying, let's get a minimally functional prototype and then iteratively improve it. That way you know it works in some context. Maybe it doesn't work perfectly, get into spiral development. We just published a couple of papers this last year on spiral development. The idea with spiral development is you start with a design that just barely works. It just does the minimal success requirements. Once you do that, you then have a baseline. You go through spirals, all the design reviews, all the stakeholder buy-in, resource acquisition, everything you need. You go through all of that, you add a feature, or you fix a problem, or you add another vehicle to the fleet. You bring in swarm optimization, all of that. This goes beyond manufacturability. It includes assembly, integration, verification, and maintainability. One of the important things to point out, though, is that this does not exclude design for manufacturing or design for manufacturability. It includes it. Because if you have just one part and you don't have an interface between parts, then design for realizability is the same as design for manufacturing. Got to keep that in mind. We can use both the classic design for manufacturing ideas and the new ones, say for example, the minimally restricted design for manufacturing, which my group has published quite a lot on over the years. This integrates constraints early, the geometry, material processes, human factors, and testing. We go in and we intentionally exclude design candidates from our consideration by excluding ones that we know will not be manufacturable. Under this context, design for realizability, minimally restricted design for manufacturing, manufacturability is the most important requirement for the system, or realizability if it's a system with interfaces. That's the most important thing. You actually get cases then where things like cost and performance are actually constraints. They're not objectives. The objective is a manufacturable system or a manufacturable part. We can worry about if it costs too much or if it is not maybe as good in performance as another product, but we know we can get it. This shrinks our design space down quite a bit, but we know when we get our designs from this, they are going to be manufacturable. We're going to go back to this talk. I'm going to do this in 5 sections. First section, we're going to talk about concept of buildability, how realizability reframes design thinking. For section 2, machine level realizability, mechanisms and assemblies. For section 3, vehicle level. 4, talking about computational AI enabled design feedback loops. Because bringing in AI and LLMs and all of that is going to be a really important enabler for us to be able to bring realizability-driven design into being. And then we'll talk about some future directions and vision for this process, for this idea. Okay, section 1, concept of buildability. Here's the basic idea. Design begins where constraints are known. This is an important thing for us to keep in mind. We can have an objective, we can say, here's our concept, we've identified a problem that needs to be solved, whatever. You don't have a design until you have requirements. You need requirements to tell you what resources are needed, what problem to solve, and what the success criteria is. This is something a lot of designers leave out, is a defined, clear success criteria. What is the criteria set for a successful design? It could be a checklist, it could be metrics on performance, it could be metrics on cost, doesn't matter. What is a successful design and what does that look like? Traditional design education emphasizes creativity first and feasibility later. We don't want to do that. We want to define what our boundaries are, and then we say we can be creative within that space. We'll be less creative than, for example, if we went creativity first. But then on the back end, we're not trying to spend months or years doing rework on the design in order to make it actually be able to be made. In practice, realizability demands early coupling of creativity and constraints. It's extremely important for us to make sure that our constraints are the most important thing at the beginning. Whenever you do a design or decision-making or optimization problem, you always have objective, usually in the form of an objective function. You have your constraints, and you have your decision variables. You have to define all of those. My takeaway from this is we need to define the constraints first, not the objective, because that puts boundaries on the objective, and it prevents us wasting time going after things that cannot be made. The constraints, geometric, material, process, environment, we're going to use these as enablers. If you go and look at a couple of the papers I published on minimally restricted design for manufacturing, one of the perspectives that we took was that when you consider and map in manufacturability constraints into part design, you're not only you're not only preventing mismatch, but maybe you have identified something special about that manufacturing process that actually is a benefit to your design and your creativity that you didn't know about before. So bringing in detailed knowledge about the manufacturing process can be an enabler, not just a constraint. Shifting the question, can we build it, to how do we design it so that it can be built? This is a really important distinction. Here is the basic idea for what we're looking at in design. This is the 5-step version. You emphasize first, meaning that you understand what the problem is, who is it helping, why is it necessary. We always need to ask when we're doing actual design. This is the difference between doing design as an engineer and doing design as an artist. An artist says, what can I create to express something? An engineer is, what can I create to help people or to solve some kind of problem? Really important decision. We define as our requirements, we ideate. How I define this, whenever I'm teaching capstone or a senior design project to my students, I always tell them the ideation phase is extremely important, because this is the phase where you take your constraint set and your objectives and you come up with a set of design candidates. So these are possible designs that work. Typically what we end up with these senior design projects is we have 3 candidates that we have the students do. Usually one of them is good, one of them is good but really expensive, and one of them is really cheap but doesn't meet the requirements. So typically we have them do that so they understand what's going on here. But the basic idea here is you're narrowing it down to 3, 4, 10, 50 design candidates. From there you're going to go through and do the decision-making process to choose which one you're going to build, which is where you get the prototype. Then you test, you implement, product on the shelf, however many loops you need to be able to get this to work. The thing is, the more time you spend at the beginning of the process, think of like building a house. If you build a weak foundation for a house, doesn't matter how nice the house is, it's going to fall down. The more time you spend at the beginning, and the more information you have at the beginning of the design process, the more reliable your parts are going to be. There still may be rework. There still may be issues with the designs, but it's going to be a lot less than if you were to actually kind of neglect the early stages and then try to just go to a prototype quickly. That is a major temptation in commercial design, is we just need a prototype. It just needs to be able to demonstrate what we need. I have all kinds of stories about early tech companies. You guys are familiar with Boston Dynamics, the robot company? So my cousin worked there. Their early robot dogs, those demos that they put on, well, it turns out that they were still working on the bugs with the software, so they weren't walking around. They were hitting QR codes all over the place, and the robots were following the QR codes. If you go back and look at from like 2012, 2015, and you look at some of their videos, they pre-programmed it to look like the dog is walking around, but in reality, there's QR codes that are hidden that the camera can't see, and they're just following it around. It's better now. Okay. Looking at this from a manufacturing perspective, a manufacturing building perspective. DFM principles. So, looking at the evolution here. We started with regular design for manufacturing, assuming the parts that we made. This was developed in the 1960s to the 1990s with the idea that we're going to essentially avoid complexity in our parts to ensure that they're manufacturable. There's a whole bunch of rules or laws around design for manufacturing, or design for manufacturability, depending on which handbook you use. But essentially the idea is common in sheet materials. If it can be a wood block with a hole in it, that's what it should be. You don't try to optimize it. Just make sure that it's as simple as possible. If you can buy it, don't build it or design it. Prevents complexity in systems, but you can realize it. That's a really big problem when we're getting into computational design. Because the whole point of computational design is to do exactly the opposite and to prioritize optimality over simplicity. How do you balance this out? Well, design for additive manufacturing has become a big thing. Unfortunately, though, as the processes are starting to get more, the technology is kind of plateauing at this point. There's not a lot of new things to do in additive manufacturing these days, besides software controls and design. Not a lot of new technologies related to this. Most of the patents for the standard processes are now starting to expire. It exploits new design freedoms, but it's a narrower perspective. We're working on an idea called design with additive manufacturing. I just published a technical paper on this 2 months ago. You can go find it on my Google Scholar if you want. Manufacturability-driven design is a thing that I'm working on right now. This is where you map in the constraints. This is what I was talking about before. If we take that and say, all right, how do we apply that to a system? The most important part of a system is the interfaces. Because you typically assume, if you look at system engineering theory, you typically assume that the individual components are well designed and they perform well on their own because they were designed, they're well refined and they were designed by group of specialists. So when you assemble it, the interfaces are going to be the weak point. That's a really important thing to keep in mind. The interfaces are the most important part. Therefore, if we go to realizability-driven design, it unifies design and manufacturing, all of these, and system level constraints, and you make sure that your system can actually be built. By built, meaning it can be all the individual parts or subsystems can be manufactured. You can put them together, you can assemble them, you can integrate the components together, especially when we're talking about control systems. I'm not going to talk about it very much here, but if you look at basic system theory, there's 3 kinds of interfaces in most systems. There's physical interfaces. This is where parts are touching each other, or fluid is being exchanged, fluid exchanger, things like that. You can have control interfaces, meaning actuators and control systems. And then you have information interfaces, which are your sensors throughout the system. They give you information. This does expand the scope from component to system realization. So this would help us go from, say, building a battery to building a whole EV, a really good EV. This is a perspective that we can take. It's going to be slower, but you know when you get to the end, what you're going to get out of it is going to be good and manufacturable. We want to bridge the digital-physical divide here, because as I said before, AI and physical tools, LLMs, are going to be a key enabler of us being able to do this. It's really important for us to use these tools and to use them properly. To speed up what we were already going to do and find patterns and data that we missed, but not to replace our brain. We're looking at digital models versus physical realities. This is where things like digital twins can come in to help. The more detailed the digital twin, the better this is going to work. This also dramatically reduces the cost of us being able to go in and do this kind of design. We look at simulation in CAD, it assumes idealized materials, boundary conditions, and precision. That's a really big problem. Maybe we need to start doing kind of a fuzzy CAD type of system, where you say, okay, well, there's some amount of deviation or interface uncertainty in the interfaces that we have. Physical processes do induce tolerances, warping, and assembly variation. Anyone who's worked in manufacturing or worked in a machine shop, when I was younger, before I went to university, I worked for 5 years as a mechanic and as a machinist. I actually wasn't originally going to go to university. It was kind of a late decision to do that. This is something you encounter all the time. Even when you have extremely high quality machines, you're going to have these issues. When you're getting into manufacturing really tiny scale things, like semiconductors, really important thing in Taiwan, this is going to get even worse. Because you're getting down to a scale where your physics changes. You don't even have classic physics anymore. Everything changes. Realizability bridges this divide. You can use digital twins, feedback, empirical correction. One of the basic ideas here, and we're going to dig into this more, is as you are doing this design, you're continuously sending feedback, and you're updating digital twins. As you are going through this design process and making mistakes and having to do rework and all of this, you are feeding that data back into your design process, which prevents the problem from happening in the future. If we bring in spiral development, that helps even more, because every spiral we're refining the design. And we're refining the design process. So the next time we need to design a system, it's just that much simpler. The goal here is predictive alignment between digital design and physical execution. That predictive alignment is extremely important. What do we want to get out of our design? And what do we actually get out of it? What is our objective to get out? And what do we actually get? How do these align? Or how do we at least reduce the misalignment? This is a really, really big problem when we're getting into any kind of computational design, topology optimization, large scale control systems, things like that. One of the main tools for us to work with this is called early constraint integration. Again, I've said before, one of the most important things for us to keep in mind is that if we're doing a sort of a linear design process, the more time and attention and resources we spend at the early stage, the more reliable and easy, problem-free the later stages are going to be. If we go in and put our constraints in early, this gives us a constraint-driven design process. Embed process knowledge early into design, incorporate the process rules and resource limits at the concept stage. Yes, your design process is not going to look as pretty as it might if you were just doing computational design. But you have a high level of confidence that what you design and what you put into the design process is actually going to be a successful system at the end. Extremely important. This is a typical process, system development life cycle, going through doing planning, design, development, and all the way around. All right, section 2, machine level realizability. How does this apply to actually doing machine mechanism design? All right. One of the big things when you're doing any kind of realistic machinery or mechanism design is you're going to have subsystems. You're always going to break down your system into subsystems. It's just too inefficient otherwise. Even if you're designing something like a transmission for a car, then you're going to have subsystems. You need to work to look at where precision meets practicality here, because you're going to, if you spend too much time making the tolerances perfect, you're going to have a really nice assembled machine, but it's going to be really, really expensive. Doing the validation and doing tolerances is really expensive. I think I saw a study one time that improving tolerances by 1 decimal place on a drawing costs 40 times as much to do the manufacturing process. That may be for specific machining processes, but that sounds about right. Machines combine mechanical, electrical control systems. They each have their own constraints. So this is an important enough thing when we're doing just mechanical design. If we're looking at just how do the gears mesh together, how do you transfer energy, how do your belts work with each other, how do you lubricate, say, designing a transmission. But when you bring in real mechatronic systems where you have electrical components, you have even chemistry going on because you have your cooling fluids and all of that, extremely important for us to keep the tolerances in mind here. Realizability requires aligning structural design, actuation layout, and serviceability. So actuation layout is really important. Remember I said before there's 3 kinds of interfaces in a system. Actuation is going to be the control interface. How do we actually control it? Going back to an automatic transmission. All the cars I've seen here in Taiwan so far since I've been here have had automatic transmissions. An automatic transmission, you have a thing called a clutch pack. So in other words, when you're shifting gears, there's a set of smaller gears inside that compress. And those actually help you shift and help you to work with a particular gear that you need to be in. It prevents you having to use a manual clutch. Well, how do you actually control that? There's a whole set of solenoids and fluid, pressurized things. It's electrical and mechanical at the same time. It's really, really important. If anything goes wrong, even a little tiny thing goes wrong, you're going to have major problems. Small geometric decisions such as bolt access wiring, stiffness gradients determine the overall thing. If any of you have driven a unibody car versus a body-on-frame car, say for example a RAV4 versus a pickup truck, it drives very differently because of the way that you have the stiffness and you have the tolerance chain going through there. I drive a pickup truck at home. I used to drive a smaller vehicle that was unibody. You can very much tell the difference in how this works. Okay, tolerances and assembly chain awareness. When we're looking at this, tolerance stacks are important enough when we have 3 or 4 parts. When we have hundreds of parts in the system, and we have mechanical, electrical, chemical, all thermal, all of this to consider, it's really important for us to make sure that we know what we're getting into. All of these are going back to what I talked about at the beginning. The more information we have at the beginning of the design process, the more successful it's going to be, and the smoother the later phases for the design review. Looking at integration and routing, I'm working on a project of this right now to put manufacturability constraints into doing packing and routing for EVs. The basic idea here is you're going to look at your three sources of information, or three sources of interfaces in your system. Not just the mechanical interface, which the mechanical interface can include a direct drive chain, a transmission. You could have fluid flowing. If you have a hydraulic motor on your vehicle instead of an electric motor, that would be a physical interface. The control interfaces and the information interfaces, so actuators, sensors, all of that, all of these have to be packed and routed together. You have to worry about the thermal constraints. You have to worry about the manufacturability for each thing. But one of the things we're finding, the deeper we dig into this, is becoming more and more and more apparent that the interfaces at the ends are the driver of reliability here. The interfaces are the most important part of the system. Therefore, that goes back to our design for realizability. If we can identify and work with the interfaces, we don't even have to necessarily design the harnesses or the pipes that are moving the fluid around. It could just be that we are going to design just the interfaces at the end and then just use commercially available other hardware. That is a very useful design process. This may not necessarily make it optimal. However, we know we can start building EVs, we can start building self-driving cars, autonomous construction equipment, things like that. Even if it's not perfect, at least we know it works and we can iteratively improve it over time. Looking at feedback loops and design validation, extremely important. So if we're looking at here at, let's say, a topology optimization problem, well, we're going to start with this. Most topology optimization problems either start with a design space and you have your boundary conditions, or it's an old part that's designed that works and you know where the interfaces are. Say where the bolt holes are and things like that. You're going to take it and you're going to say, all right, well, let's do our design process on it and look at our design candidates. Typically, when we're doing topology optimization, there's one of two objectives. One is remove as much material as possible while maintaining stiffness, and the other is remove as much material as possible while maintaining a certain level of stress in the part. However we design that, we get our part out, okay, we have this one design iteration. Now we manufacture it, and we validate it, send it back through. One of my PhD students and I right now, we're doing a review paper on design experimental validation for topology optimization solutions. And one of the things that we're finding is that even people that are claiming to be able to do this are not doing it properly. They're missing a whole bunch of information, and they're doing really ad hoc design. Ad hoc design is where you say, and I'm sure you've probably seen this before, where you say, okay, well, here's my design. Well, that thing didn't work, so let's change one little feature and try it again. Well, maybe that one doesn't work, maybe it's better, who knows. Just try it. You need to go back and do corrective iterations. If we were to bring in design for realizability into this, which for a single part, it's the same as design for manufacturability. If we bring this back in, we're collecting data every time we do an iteration on this, and the data is useful beyond just the individual part design that we're looking at. We can look at things like what's the minimal feature size, how do these designs interact with specific manufacturing processes. Are we going to 3D print this? Are we going to machine it? Are we going to cast it? Are we going to injection mold it? We're collecting data. We're going through this feedback loop, and we're going into the whole system design by understanding the interfaces. Because you're never going to have a part like this that's just standalone. Unless it's a piece of art, it's never going to be standalone. It's always going to interface with something else. We can probably assume, based on the pattern here, that there's going to be at least 4 mechanical connections. Could be a cable, could be a bolt pattern. There's going to be a lot of options. All right, what if we were to take this now from just a machine and mechanism and then move this into actually doing vehicle design? Because that's ultimately where we want to go. That's one of the biggest problems that we have now is how to make better vehicles. Whether it's military projects, whether we're trying to make self-driving cars in cities, trying to make buses, better trains, all of that, we need to think about vehicle level. Because the vehicle level is the kind of the ultimate system design perspective, because you're interfacing, not only do the parts inside interface with each other, but now the vehicle interfaces with the environment and interfaces with people. Those are two places where even a really good design can break down really quickly. So we need to consider those when we're looking at vehicle realizability. We're looking at machines to mobility. So think of, we have one level of design. This is going to be our transmission, or our drivetrain, our rear diff on the vehicle. Now we expand that to a higher level, and we say, all right, well, how do we design the entire vehicle? How do we take all of these things? You have a transmission, and a diff, and a transfer case, and an engine, and all the sleep pumps inside the vehicle, and the control system, and the electrical system. How do these all fit together with each other? Well, this is one way to look at it. If we're looking at the operating environment, we got a driver, road, vehicle, kind of, the way that this is set up, it's almost like a trinity kind of thing. You can't separate any of these because all of these affect the design. All of these go in and tell us, do we have a successful design or not? Goes back to what I was saying before. What is our success criteria? That's something designers need to always ask. What is the success criteria? If you go back and look at some of my papers on this, we actually have sections at the end that says, good design was successful because of these three things. Those are our success criteria. And when I'm teaching design classes or looking at senior design projects, we always tell the students, go through, write down what is your success criteria. It also helps them decide when the project is finished. That's really important. We look at system level constraint coupling. We talked about the constraints of the individual parts and individual subsystems before, how the constraints interact with each other. If you're putting together a diagram like this, so engine, clutch, you have motors, you have your various transmission diagram, and it goes to the load, meaning the wheels. Okay? Well, you have a motor running this, you have a motor running this from the clutch. The motors could be actually working with the clutches. You have a whole bunch of different things, different tolerances, different sources of tolerances. All of these have to work together. You also have to lubricate, and you have to cool it. Really important. Any of you who have ever worked on a transmission, or you rebuilt one, or seen it done, you make one little tiny mistake, you're going to have major problems. Operational environment is really important. My group published a paper at the last IATC where we went through and we said, all right, if we're looking at an autonomous construction system based on warthog robots, and we put in an environment like this, how is it going to affect the performance? How is it going to affect the positioning, the reliability of the system, all of that? Again, when we talk about vehicles, you are interacting your design with humans and with the environment. The environment is brutal and unforgiving. If it can break, it will break in this kind of environment. So we have to consider this when we're looking at it. Even if it doesn't break, we're going to have performance degradation. It's not going to work as well. It's going to be harder to maintain. It's going to be harder to repair. It's going to wear out faster. If it's in a saltwater environment, if it's in a really cold environment, or worse, you have really extreme temperature swings, you're going to have all sorts of issues. Even worse if you're trying to bring in EVs. One way we can look at this is, again, using digital twins and autonomous verification. One of the things we want to try to look into actually is, there's a lot of good digital twins that already exist for individual manufacturing processes and individual components, such as engines and transmissions and things like that. Are we able to actually stack and assemble the digital twins like we would the real system? Is that even a thing? We need to look into that, because doing a full digital twin of a vehicle this size is insanely expensive. It costs millions of dollars to build this. You have to get a real vehicle, model everything perfectly, put sensors all over it. This is one of the projects some of my collaborators in the US are working on, with a big Cat D9 bulldozer. Put hundreds of sensors all over it and try to build a digital twin. Maybe a more efficient way, if we're looking for a good enough or functional design, is to take the individual digital twins and stack them together. That might be an option. We need to look into it. All right, section 4, looking at computational AI-enabled design feedback loops. This is where we start getting into trying to use our AI tools. My perspective on using AI tools for design is that they're useful for two things. They're not useful for doing the design. That has to be our own brain. It has to be human creativity. They're useful for identifying patterns and interfaces that we didn't know about before. And they're useful for speeding up phases of the design process. Say, for example, defining requirements. We define the requirements. AI can help us to figure out how to validate those requirements. Doing a verification and validation on the actual system, really important. This can really help us speed up that process because it's all about decisions. One of the things I tell my students whenever I'm teaching an introduction to whatever engineering class, I always say, okay, what is your definition of an engineer? What does an engineer do? The definition that I like to use is an engineer is someone who makes technical decisions under uncertainty with imperfect information. That is a good way to describe what we're looking at here, and maybe some of the gaps we filled in with these AI tools. Because if we're looking at a data-driven decision process here, and we need data to do the AI, of course. You define the objective, you establish a hypothesis, what are you going to test? And it's really important when you're doing a research hypothesis to have something you can actually test. Because one of the definitions of science is that it has to be falsifiable. Meaning you have to be able to disprove it if it's wrong. Identify data need, build the data process, collect your data, analyze it, and then make a decision. And this is an iterative process. You do it over and over and over and over again. This is a long, drawn-out process. If humans are doing it, AI can do this very, very quickly without introducing any major errors or problems. Obviously, we need to supervise it. We need to keep an eye on it and make sure that it's giving us what we want. This is what I'm trying to work with my students right now is how to use things like ChatGPT properly. In our undergraduate classes, say the first and second year and most of the third year classes, they're not allowed to use it at all because they need to understand the basic ideas first. When you start getting into your fourth year classes and even some of the high level 3-year classes, and you're getting into graduate programs, you should be using it all the time as a tool. Once you learn what you should expect to get out of the tools, and you learn how to set them up properly. In a graduate level course that I teach on advanced manufacturing processes, I actually have assignments where the students are required to go into ChatGPT or Claude or one of those AIs, have it solve a problem for them, and then do a technical evaluation of the output. And a lot of times the output that it gives them is trash, and they have to catch it because they have the basic knowledge to be able to do this. Okay, constraint aware optimization, going back to this. We say, all right, well, can we take what I talked about before, the basic concepts of constraint-driven design? So you're driving the design with the constraints, not with the objective. It's the opposite of how you normally do design, but it opens up a whole new class of problems we couldn't solve before. If we look at that, we say, all right, well, constraint-aware optimization, we can now maybe go back to these computational tools that we talked about before that had problems. Well, maybe we can eliminate some of these problems by finding the sources of the errors using the AI tools. Really important, a really important tool for us potentially. We learn from the factory floor, what are we actually getting here? This goes back to, remember what I was talking about with the vehicles? We're continuously collecting data. And that data is continuously improving our process and improving our decision making. We need to do that not only for the vehicle in the field, but when the vehicles are being made as well, because that feeds back into a good information loop back into our design process. Look at human AI collaboration. So keeping the engineer in the loop, of course. We are going to be publishing a paper hopefully early next year on maybe some more responsible uses of AI for this. And we want to keep the engineer in the loop. We want to always make sure that a human is involved. Somebody has to be able to shut it down, interpret it, figure out where something goes wrong. You'll always have humans in the engineering process. You can never completely remove the human element. AI identifies feasible zones, humans interpret the trade-offs in context, because sometimes the best decision to make is one that's not purely logical. Therefore, a human has to make that decision, not an AI. The AI can be informed. Let's go back to our definition of an engineer. Someone who makes decisions under uncertainty with imperfect information. So that brings up two questions here. How do we reduce the uncertainty? And how do we get better information? You'll never have perfect information, but we can get better information. As we go along, we can collect all of this data. Operating models for vehicles is a good example of this. Let's talk about the future directions and vision. All right, looking ahead, the next frontier of realizability is going to be bringing this into making more complex and better systems. This is going to be extremely important when we're getting into, feeding the AI by building data centers, figuring out how to take care of agricultural problems all over the world, how to get better farm equipment, better construction equipment, how to make the world safer for people, how do we remove problems, do disaster relief, all of that. Realizability will evolve from a rule-based adaptive to self-directing systems. Rule-based, that's going to be heuristic design. If, then make this decision. If this, make this decision. To a adaptive, meaning we learn over time, so it's the Bayesian type of decision-making process, to a self-directing system. It's an AI that we train, and then it trains itself to be better over time. Digital twins will continuously synchronize design, intent, and field data. Remember, going back to our alignment. What do we want? What do we get? How do we make sure they're aligned with each other? Future design environments will integrate physics, data, and context awareness in real time. So it's going to be able to go in and actually take data from sensors and make decisions on the fly. Even if those decisions are physics informed or human informed, or at least a human sitting with a kill switch if there's a problem. We want to shift from can we build it to can the system build and verify itself. That is something probably that's going to be a thing in the future. You've heard, I'm sure that you all heard the meme about 3D printers making more 3D printers. How 3D printers reproduce. They just make more of each other. Kind of the same idea. Looking at cross-domain impacts, this is not only in mechanics and design thing. This is going to bleed out into a whole bunch of other areas. So when you look at beyond machines and vehicles, these principles of realizability extends to construction, aerospace, energy, marine systems. Energy is going to be extremely important in the future. Common theme, coupling between the structure, material, and environment. Environment in this context doesn't mean like green, like a green technology. It means what is the actual operating environment of the vehicle itself. It does help making things more efficient, but for now, we want to make sure we have a vehicle that works, and then we iteratively improve it over time. Some of the applications, autonomous concrete printing systems for expeditionary construction. That's an area where I'm working with a lot these days. Energy-aware robot fabrication, remote and underwater settings, self-verifying AM components for marine maintenance. All of these things are what we would consider expeditionary manufacturing. Or, as one of my graduate students is working on right now, good enough manufacturing in dirty environments. I talked to in the United States, DARPA, DoD, Navy, NIST, NSF. All of them are really interested in this. How do we make a design that works and it's not perfect? It just needs to work, like right now. So I'm working a lot with the Society of Automotive Engineers these days. I'm an officer in that society, working with IDM, vehicle design and decision making, and we're trying to bring a lot of this stuff into that right now, because the Society of Automotive Engineers is really, really interested in this. Realizability provides a unifying framework for multi-domain engineering. This helps us to put together what's called a technical dictionary, meaning if we have a bunch of experts from different domains and different levels of expertise, we can put all of their language together. And this is, you might have a mechanical team, an electrical team, and a cooling team, like a heat transfer team. They can't work together perfectly because they're using the same terms to mean different things. So if we were to use realizability as a way to build a technical dictionary, we can say, here are the team members, here are the stakeholders for our design. How do we actually make sure that we're all speaking the same language? And that we all mean the same thing when we say certain things? Maybe realizability is the framework for putting that together, which gives us the ability to more efficiently take care of the problems. I mean, this is one of the things that's a big consideration right now is who should be doing this design work? Who in the world should be doing this? Which countries should be involved? Can countries do this work for the benefit of all of the world instead of just themselves? My attitude is more brains equal smaller problems. Everybody who can work on this should be contributing. Everybody's ideas are important, but we all need to make sure that we all mean the same thing and that we understand what the others mean. Looking at it from an educational and cultural shift idea, going back to realizability, so we need to teach the next generation to design what can be built. We should prioritize realizability and not design elegance. Design elegance is for the artists. We need to make a vehicle that actually works. Engineering education should bridge simulation and physical realization. A lot of engineering degree programs do not have the students actually do anything with their hands. They just go to class, they watch a teaching assistant do experiments in the lab, they learn how to program and they learn how to do a little computational design. They never actually go and do anything. That's one thing I'm really impressed with this university as I'm being given tours around. Students everywhere, just doing real stuff. That's a rare thing in the world, and it's something that is a very big benefit to you as engineers. When emphasizing constraint mapping, digital physical integration, design verification in the curricula, we need future engineers to expect that they need to think about these things when they're doing their design. Because at the end of the day, most engineering jobs are going to be related to design in some way, shape, or form. Students should experience failure modes as part of learning. So we can call this learning like realizing. We need to start teaching engineering students that failure is an important part of this process. Their designs fail, they miss some important thing in the design that made their vehicle not work. That's not a bad thing. That is part of the education process. It's part of building the intuition toward design for realizability. Because failure is part of life. When you're doing design, you're always going to have failures. But you can have fewer of them over time if you learn from the ones that you do. Broader cultural goal, elevate buildable design as a creative and ethical ideal. So right now we can say, all right, well, what are the ethical points of design? Well, we want to design for efficiency, energy efficiency. We want to design for green. We want to design for human systems, all of this. Maybe this is something that can be added to that list. Here's our vision as a summary. So designing what can be built, building what can be trusted. Trust is a really important part of verification and validation. When you're working for a company, or you're doing research, or you're working for a government lab, your clients or your customers need to have confidence that the thing that you're building is going to actually work. This integrates human creativity, computational intelligence, and material reality. Material reality, going back to what we talked about before, there's no such thing as perfect information, and there's no such thing as perfect materials. This enables resilient, autonomous, and verifiable engineering systems. The future of design, I think, should be where every concept can find its place in the real world. We just say, instead of saying, well, your ideas are no good, or this is not ever going to work, we can just say, your ideas are valuable. How do we make them useful in the real world? Because there's a distinction between useful and valuable. This is when we go back to utility theory in decision making. The stakeholders decide what the utility is. Utility does not necessarily mean value. It can mean usefulness as well. Here's my call to action. Here's what, if we're taking away from this talk, here is what I would like for us all to do, to think about. We want to rethink our design goals. We want to move beyond performance metrics, define success in terms of buildability, verifiability, and longevity. Again, we're building trust. We're saying, if you give me a contract, or you hire me for your company, there's a high degree of probability and a high degree of trust that what you get out of working with me is going to have utility for you. Utility could be making money, you're reducing loss, or just general usefulness. We want to build feedback loops and everything, not just when we get to the end of the process, but you're taking data continuously. AI tools and digital twins help with this a lot. And we want to cultivate realizability thinking. We want to say, when we're doing engineering design, the final product is not the design. The final product is the product working in the field. That is really important. All right, thank you so much for your attention and time. Here is my contact. Feel free to connect with me on LinkedIn to this QR code. I'll be happy to answer any questions or stay around afterwards and chat if you want.
Okay, any problem?
So I have the idea
I'm going to, so my answer to that is I hope so. Yes, that would be wonderful. I'm
So
not yet to the point where I'm completely confident in that, but that would be wonderful if we could.
If we can do that, I mean, we can optimize exactly. So that would be interesting. I'm curious about what's the good example, good application that we can quantify realize, and then show people how we enhance the level of this realizability. This, or I don't know how to pronounce.
I think that would be probably the most pressing and the most socially valuable system is going to be transportation systems.
Okay.
That's going to be not low hanging fruit, but that's something we can start tackling immediately.
Yeah.
And this is something we can start working with. Now, a realizability metric, I can think of two ways to approach this. One would be it's wonderful to be able to do this. But on the other hand, I'm sure you've heard the expression, if it can be quantified, it can be gamed. So do we have people that would try to make it or to cut corners? You know, we need a standard for how to do this. This right now is just conceptual. I would say yes, we want to do that, but there needs to be an agreed upon set of standards that we follow. Otherwise, there will be people who find shortcuts, and then their designs will fail, and then this idea will get a bad name.
I like that.
Okay, any questions? Thank you.
So I'm curious with the beautiful design. So that also for the beautiful different depending on the manufacturing technologies.
Right.
Maybe so it means it can implement the real society. Maybe so it is interesting beautiful designs.
This is one thing I wasn't going to talk about this, but so in my opinion, so there's various accreditation agencies for engineering schools that kind of they drive what engineers think because of how they accredit the degrees that you get. It's all over the world. Maybe professional society should be managing this instead of these accreditation bodies, and maybe looking at this from a professional society perspective might be a good approach to what you're talking about. Do you agree?
I agree. So because using the additive manufacturing technology, so all shapes are beautiful.
No, I'm actually not. So I've been working on additive manufacturing for about 12 years now, and I've completely lost confidence now. Yes, it's a good tool if you use it in whatever context. But in my opinion, in my experience working in manufacturing, I think we're going to level off if we consider additive manufacturing as just all family of, it's 80 or 100 different manufacturing processes, all in different families. If we were able to integrate these, right now there's only two processes that really do well in manufacturing. That's going to be wire arc additive and then FFF. Those two have been widely implemented in real manufacturing. Both of them have problems. Both of them are a lot more expensive than traditional processes that do the same work better. So additive manufacturing I see as an enabler of technology, but I think that we're going to eventually get to the point where it's not a hot topic anymore. It might be 5% of manufacturing. I think that my prediction is that it's going to go back to what it was in the 1990s, where 75–80% of manufacturing is going to be machining, casting, and injection molding.
Okay.
Yeah. But additive manufacturing can be used to make the tooling.
So I believe this is the gap between the design and the how to manufacture. The tool still have another game, but I think the technology is keeping going. So in the future,
Let's hope.
Okay.
Let's hope. But we're going to
ideal
discover new
manufacturer process, ideal material, then we can do anything.
The problem is we kind of have to go with the assumption that every material and every bit of information is flawed in some way.
Okay, so any other questions?
This is why continuum mechanics doesn't work in the real world. Because you have flawed materials.
No, as you just mentioned in the beginning of your talk, the design is always perfect. Yeah, but this is how we are going to do the optimization. Go to the iteration during the process. So the first prototype is always lousy.
Well, one funny thing to think about is, and this is, if any of you are artists or you have artists in your family, this is a joke, it's not anything serious. But you know why artists have such big egos and engineers do not?
Why?
Is because artists think their designs are perfect and engineers know they're not.
No. Okay. Even though the artists can make some mistakes, so you can become a masterpiece.
But the thing is, yes, but the thing is, in this context, mistakes actually, even if the design fails, we get data.
Yeah, right.
So that is still successful in some form because we're learning.
Right.
Just keep in mind, as engineers, your learning process does not stop when you get your degree.
No,
You have to continuously
your
learn.
entire life.
Right.
Even after you
Especially when you're getting your PhD degree. It's just the beginning.
Well, there's always the jokes about engineers never retire.
No.
Right. They work until
Okay.
they die. Yeah.
I just have one perfect example that one of our professor just got retirement like 2 years ago. He still attends. His life is so angry. Any other questions? It's okay. We'll discuss. Okay. So thank you for a very interesting topic. Maybe we can start go brainstorming how to collaborate with me. So the first keynote is finished right now, and we will have a coffee break outside. And next keynote we invite Professor Osawa to. So after the coffee break, encourage all of you to attend the next keynote. Okay, thanks a lot. Thanks again. Thanks.
Thank you for the information. I want to share these.
This is why
I'm going to send you the proof.
I mean, this is why. Yeah.
Sounds good.
This is why